Hello, good evening, everyone. Um, my name is Dinis Rosário. I'm senior software developer at Miniclip, and I work at the server team of 8-Ball Pool. 8-Ball Pool, if you don't know it, you never play it, you should play it. And it's a mobile and web multiplayer online game. Me and my two colleagues, we are a team of 3 members. We manage more than 20 game servers and other servers that works for GamePods, send push notifications and social features and chat servers. And obviously, it runs 24 hours a day and 7 days a week. And it runs on Erlang. This talk is about Erlang. Anyone here know what is Erlang? Great, great. And Elixir? More people, yes, right. So this is about Erlang and how the Erlang module of Let It Crash has led us to a reliable system. So Let It Crash and reliable system, what the hell? Reliable software doesn't crash, right? No one expects a reliable software to crash. But in reality, we all know that normally hardware has errors, right? Software doesn't have errors. Networks are unreliable. Sometimes programmers make mistakes, and normally, well, usually we don't have bugs, but in a very rare case, software has bugs as well. So everything is like a perception and a reality. So instead of denying what the real world is that software has bugs. System will fail, okay? We acknowledge them, and we don't want to have uncontrolled failures. And Erlang will give us a tool and powers that turn those failures and exceptions and crashes into something that we can use them and control, okay? It's like fighting fire with fire. So everything is about control. If we can control the failures, they are stop being scary, right? Because I know I can control it. So when it fails, I know it will fail in a way that I know what will happen. Because not everyone knows what is Erlang. It was a technology that was researched and developed by Ericsson in the 80s. So it's more than 30 years. It was meant to build PBXs, this telephony switch. It was battle tested with a number of Ericsson products, and I need to show you this, that one of the Ericsson product is an ATM switch. It has 1 million line of code, of Erlang code, which is a lot for Erlang. You have a 99.999% of reliability. That's 99. It means 1 second of failure, of downtime in 20 years. How many backend engineers here, server developers, no one? Oh yeah. You basically know what achieving 99.9% is very hard, right? It means 2 hours of downtime in a year. It includes patching. Achieving 99 is crazy, right? And Erlang actually open source since 1998, which is very nice. And nowadays it's used from different domains, not only in telephony. It's used in banking, trading systems, gaming, and web applications, and others. So who actually use Erlang? I don't know if you know WhatsApp. WhatsApp now is a Facebook company, but when Facebook bought them in 2014 for 19 billion US dollars, okay, they have 465 million monthly active users, and they process 430 billion messages per day. But what is more impressive is this one, okay? We have a company of a massive backend, and it's only maintained by 32 engineers, okay? When I'm seeing this, I feel that I'm in a team of 3%. It's actually much more than 32 engineers for the entire WhatsApp. It's crazy. Don't know if you know what is Bet365, it is a betting system in the UK. They have 20 million users and more than 1,000 concurrent users at peak time. And Goldman Sachs using the high-frequency trading platform. And of course, Miniclip. These guys over here, okay, me at Able Pool, we have more than 10 million daily active users, and we have more than 500,000 concurrent users at peak time. So these guys of Bet365 is small for us. So Erlang, what is Erlang? I want to talk about Erlang. The basic building block in Erlang system is a process, okay? A process in Erlang is fully isolated. It means you can't access outside of its memory. It shares nothing, okay? Everything is isolated. So only the process itself have access to its data. And one thing is that when a process dies, it won't propagate failure to another process, okay? And Erlang process is not like the operating system process, not even threads. It's a very lightweight execution unit, and we can have thousands of processes, okay? This picture here shows what a normal Erlang system is. Okay, you can see each single fish here is a process. Okay, this guy here is me. Okay, taming the entire fish. So, process is isolated. How we can access the data? The only way to access whatever in Erlang is through messages, okay? Two processes communicate to each other using messages. And this is a asynchronous communication. So you send a message, you go back to your work, you can check your mailbox, so you have any reply, and this is how it works. And this is very critical here. Whenever you send a message, you have guarantee that you will reach your receiver. Okay, this is essential for solving a lot of problems. So, in reality, although I told you that the processes are independent, there are some dependencies, because whenever there's a communication between two processes, there are a dependency between them. There's an implicit dependency. So what it means process A send a message to process B dies without responding. How process A knows? It can wait for the reply forever and block forever, which is very bad, right? Or it can just give up after waiting some time. But what some time means? What if the process B is just taking too long to reply? So, fortunately, we have other mechanisms in the system to help us to solve this kind of communication problem. One of them is the monitor. What is a monitor is just me as a process observing other processes. So it's just a way me saying to the system, hey, I want to keep an eye on that one, and whenever he dies, drop me a message. Drop me literally that letter. So based on this, I will know that if I send a message to someone, or he will reply, or the system will tell me, oh, that guy is just that. So do whatever you want. And this is the voyeurism that the process that's being observed, it doesn't know is being observed. So. And there's another mechanism that we call link. And link, when you link between two processes, their fates are sealed. So basically, if one process it die, it will bring down another one. You know what I mean? And this gives us an architectural building construct that we can do to tie a group of processes together. So that when if one fell, they fell like a unit. It's like these guys here, you know. If this fellow, for some reason, fell, it will bring down everyone with the same link. This is the concept of link. And there's also some link. And this link is, sometimes we don't want a really bidirectional relationship. Sometimes we want to have a master process like this, like this guy here, that if he dies, everyone will be bring down with him. But if one of those children dies, he will stay where he was. So in Erlang, basically, we have a way to define that some processes are very special. So this process, instead of being killed by the system, it will trap the exit signal, okay, and convert it to message. And this mechanism here is very essential to build a mechanism that we call supervisors. And what is a supervisor, you may ask? Supervisor is just a special process, and it only do one thing. It just have the job to start the process, keep an eye on it, monitor it, link to it, and whenever that process fails, it can restart it. Okay? And of course, it can, normally a supervisor can start a bunch of processes, and those processes can be another supervisor. Okay? That's when we, in Erlang code, we have a supervision tree. So I have a master supervisor, it can start other supervisors, and the supervisors all the way down like a tree, and end up in a worker. A generic process that doesn't have this job, we call it a worker. Supervisors in Erlang have different strategies about restarts. The first one, we call it a one-for-one strategy. Basically, it's this picture here that if process 2 die, the supervisor just restart the process 2. Then we have a one for all. So the same situation, process 2 dies, the supervisor will kill all of his supervision tree and restart everything from scratch. And the last one here is, we call it rest for one. So whenever, again, this process number 2 dies, it kills the rest of it. So it kills number 3 and restart 2 and 3. Okay. Also, one characteristic of configuration of supervisor is about the tolerance, and we call it the crash intensity. What it means is very simple. It just means that the supervisor will allow a number of crashes between a time frame. So whenever a worker or one of his workers crash more than this tolerance, the supervisor itself will exit. So he will kill all the childs and exit. The reason of this is you probably have something wrong, really wrong at that part of the supervision tree. So it just kill itself and let his supervisors to decide what to do. Okay? There's obviously a top supervisor, is the system itself. So whenever everything is crashed and exit, the system will end. So we know now you basically mean that in Erlang we let the process crash, and we have a system, building blocks that will do the restart. Okay, but does it work? It depends on the type of the failures you have in hands. Some failures, like you crash because data are corrupted, it doesn't work restarting, right? You restart the process, it start over again, and will crash again, because you have a problem that the restarting will not solve it. But other types of failures, they're transient, like a network reset. Some connections get down. Maybe restarting will help you, right? You can restart, reconnect, and everything just continues. So failures basically can be roughly divided in two groups. There are some repeatable failures. Repeatable here means we know exactly what are the causes, we can repeat it every time, and there are some transient errors, that network failures. The cleaning lady plugged the plug. These are the transient failures. And repeatable failures, you need to solve it, and usually it's, well, easy here means you know exactly what it have done to fail. So whenever you know how it fails, you can fix it. And if you have QA, if you do QA, unit tests, system tests, you can normally catch all these failures before your software reach production. Even those little bastards reach production, well, it will be possible to detect them, and you can replicate it and try to patch it. But transient failures, these are the nasty ones. It's really, really hard to find it and to fix it. And normally they are so rare, you will not know it before reaching production. That's where the scary part of our jobs. And even a failure that is so small, it will occur. Here I have an example of 10 million daily active user for a 0.01%, then you will have 1,000 users that will crash every day. I can give you another example that in my previous job, we make call center software. I make a system that is do the outbound calls. We call the customers. And that system, in my part, it calls the guys and it tries to detect is an answer machine or is a human. And whenever it's a human, it transfers to the agent. And we found a very nasty bug that is a transient failure that every once in a while, one in a week, the system crashes and the call center stops. And my boss said, oh, we need to fix it. We need to fix it. This is not acceptable. We build a lot of effort. We build a lot of tests. We track down where that bug is. And we do the test. We fix it and reach 1 million calls in our test bed. So we ship it to the customer. And for a while, it's worked. But after a month, 2 months, I remember very well that one night, the CTO calls me and say, it crashed again. What have you done? And it was a C++ server, okay? And the crash is an access violation. And we eventually fixed it doing very nasty C++ code that I'm not proud of it. You want to know what I done? Talk with me later. I won't tell you here. But this just means that, okay, when you have scale, you have millions of users, you may have crash every day. But even the small system, it's just, you give it some time, and if there's some transient failure that triggers some bugs, it will crash. And when it crashes, no one knows how to fix it. So restarting, we say, will not work for repeatable failures. May not work, okay? Core features surely will not work. You need to fix it. It's core of your features. But sometimes there are some secondary features, some features that nobody uses or rarely use. Well, then depends. Restarting may help you, okay? You need to assess if it's important, sufficient or not to fix it before production. But restarting is the key of all our Erlang system. It's extremely effective, okay? Remember my example from my previous job. We spent a lot of time tracking the bug, fixing it, testing it, okay? And even that, we didn't fix the bug, okay? We reached a very high scale, but after some time, more time, it failed. And hard to reproduce bugs usually means it only happens under some unknown circumstances. Maybe some alignment between the planets and make it crash. So, does it worth your time fixing a bug that only occurs 1 in a million times? Maybe not. Maybe just restart. Well, we screw up, we restart, we move on. This is starting to make the failure disappear. We just put everything under the carpet, but it's not. You know you have some bugs here, So you can have logging, tracing, and it will buy you some time. So you can, maybe you can have more data to look at and fix it if possible. And in Erlang, as you know by now, we have a very, very good strategy to deal with bugs, with errors. And it will move us to the thing that we call here is a happy path programming. What is happy path programming? So it basically means we just don't care about the error stuff, okay? We code for the normal way, okay? We don't do defensive code. We don't do error handling. We just let it crash. Because we have a restart strategy, we have supervisors, okay? This practice, we call it happy path programming. We just do the positive stuff, okay? So when we code our system, we don't think all the edge cases, we don't have all those else to deal with errors, okay? We just focus on one thing, is what everything is doing exactly what meant to be done. So we just think about it, and whenever there's an error somewhere, okay, we know that, okay, my execution will stop there, and something will restart the execution. So we need only to focus on what is the happy path and what to do next. Does it restart? What will we do with the restart? And this will lead you to another way, okay? It will lead you to a happy path, and then it will lead you to the high-level programming. What I mean for high-level programming, you will focus on algorithms, okay? What your system algorithms do. What are the protocols, okay? What the design of your system is. And you won't spare your time dealing with error handling, validations, and those crazy code that is there just in case that some alignment happens, we won't do whatever. We don't do it, okay? We just code for the okay response, okay returns. Everything, if it crash, is an error. We have an error strategy to deal with it. So this talk is short, and you probably is sleeping and hungry. If you didn't notice, I have a TLDR for you. So one thing, remember, Erlang processes are lightweight, okay? And the only way for communication is sending messages. You will find this module as an actor model, okay? In your system, you only have actors, and the only way for communicating between them are sending messages. A failure in a process normally will not propagate to another process. If you work with Phoenix or Elixir, you know that whenever you crash your connection, it just stay there. You won't crash everything, okay? One thing that I want to tell you that everyone knows what is Apache server, right? The Erlang HTTP server is called Cowboy. Why it's called Cowboy? Because it killed the Apaches, okay? Restart, okay, can be a very, very effective way to deal with transient errors, okay? For transient errors, we mean everything. It can be some programming errors under some obscure code. It can be some network errors. Okay, something that normally won't fail, but it happens. So restarting the process, restarting the execution is a very effective way to deal with it. And remember happy path programming. Okay, Erlangers is what we call with ourselves, Erlang programmers. We are happy guys, okay? We are positive programmers. We don't think about, well, we think about it, but it's not something that we're actively worried about errors, okay? We focus on software architectures, protocols, okay? That's the fun stuff. Not doing all those cascading else's, okay? Not dealing with errors and avoid crashing the software, okay? And I won't show you the movie, but everyone should see this Erlang movie, okay? Go to YouTube and find Erlang the movie. It's a 10-minute movie from the 80s, mono, only the left channel, okay? But it's very fun. And you have the founders, the designers of the Erlang explaining better than me what is Erlang, okay? And if you really, really want to abandon C++, Python, whatever, and want to have a better life, a happier life, and want to learn some Erlang, go to this site, okay, remember? Learn you some Erlang, and that's it. That's my talk. Just give you the, well, the end earlier. No questions, right? Everyone now support Erlang. Really? No one is so bad? Or you guys really understood what I talked about? It took me years to understand this. Well, that's it. Okay. Thank you very much. Thank you for your time.